Good morning to everyone. In the project, we wanted to use a very powerful tool that is the chemical ad hoc modification of polymers through the copolymerization. It has the insertion along the macromolecular chain of a different comonomeric units. In this slide, you can see the various monomers we are intended to use in these chemical modification strategies. As you can see, some chemical formula are in green because are monomers from bio-based origin, and the other are in black because they are from fossil resources. We are intended to use most of them in our project. And we start our activity with check the importance of purity of monomer to get a final polymer colorless and with high molecular weight. And we saw that we need a very high purity, higher than 99.8%. In case we don't have it, we decided to esterify our decarboxylic acid in order to improve the purity of the starting monomer. And Stora supplied us with a different 2,5 fdca characterized by different degree of purity. We decided to check the impact of different purity on the final polymer by taking an homopolymer as a reference. Our homopolymer is a polybutylene furanoate, which is whose synthesis is described in this slide. We saw that the purity has a huge impact on the final polymers obtained. Indeed, the color and the molecular weight are strictly dependent on the purity of our starting monomer. We saw that the effect is particularly big in case of a starting monomer with low degree of purity. The effect is less important in case of a diacid with quite high degree of purity. In any case, esterification reaction reveals to be an efficient tool to improve the purity of our starting monomer, and so we are able to obtain a final polymers no colorless and with high molecular weight. Here, the characterization in terms of thermal properties and in terms of nature of crystalline phase present on the polymers PBF prepared starting from the different batch of FDCA and of dimethyl ester of this FDCA prepared by Condensia, a partner in our consortium. Here we check the processability of our polymers PBF, and we try to compression mold this polymer to obtain films and even to prepare cast film. And we were able to process easy our polymers, mainly if it's with high molecular weight. This activity was carried out by UniPG, by Professor Deborah Puglia team, and the condition of processes are reported in the table. Here, we try to extend the processability of our polymer by blow molding. This activity was in charge to Biomi, one of the company in the consortium that was involved in the preparation of Furan-based polyester for packaging application. As you can see, we got nice results, and the polybutylene furanoate has even better mechanical properties than PLA and comparable properties with respect to bio-PE, which is an important commodities obtained from bioresources. Here we see how can we use the chemical modification as a powerful tool to target the final polymer properties. For example, if you want to increase the flexibility of our reference polymer, we can introduce a diacid with longer aliphatic chains, or in alternatively, we can use linear glycol with increasing number of methylene groups, or even heteroatom containing glycols or heteroatom containing diacid, because the heteroatom sulfur and mainly oxygen increases the final polymer chain flexibility. In alternative, if you want to increase the stiffness of our reference polymer, we can introduce rigid diacid such as isophthalic acid as an example, or in alternative we can use rigid diols such as neopentyl glycol that contains two methyl groups side chain, or cyclohexane aliphatic glycol such as cyclohexane dimethanol or azosorbide. In this way, we are able to prepare a polymer with higher stiffness, rigidity. Here, three examples of copolymeric system prepared for flexible packaging. The composition are not shown, but you know that playing on copolymer composition, we can finally tune the final mechanical properties. As you can see in the first case, we introduce a glycol containing a long side chain which act as internal plasticizing effect. In the second case, we use two different linear glycols with a different number of methylene groups. In the third case, on the bottom, we use the acid containing a higher number of methylene groups in the molecules. In all these three cases, we were able to obtain flexible materials. Here you can see the thermal characterization carried out in Alicante University, another team present in the consortium. On the right, you can see the compression molded film prepared from these three systems, and even the values of water contact angle in order to evaluate the film hydrophilicity. Here we decided to design a new material able to have intrinsic antimicrobial properties to prepare car filters. We decided to use two approaches. One approach is to introduce along a macromolecular chain, long side chain, able to destroy the cell membrane. The second approach is mimic what happened in nature, considering the presence of cationic lateral chains that can interact with the anionic chain present in cell membrane, and is able to obtain the requested antimicrobial properties. So we decided to introduce a monomer that can impart to the final polymer a positive charge on one side. In the second side, we decided to introduce a side chain very flexible with a high number of methylene group. We use in this second case a glycol on the left, and on the right prepol, which is a cyclic aliphatic diacid containing long side chain. Here the copolymeric system prepared according to the strategy described before. This material have first been characterized from the thermal and diffractometric point of view by Alicante, and have been sent to ENSTM, another partner of the consortium, to be subjected to electrospinning. And we got preliminary very promising results. And now we also considered the screen for automotive applications. In this case, we need a polymer with very high TG, around 100 degrees. So we decided to combine FDCA with the naphthalenic acid. We prepared random copolymers containing different amount of the two monomeric units. This activity was carried out by Polish partner in collaboration with LCI, an Italian company working in automotive sector. We got interesting polymers which can be processed into duck bones shape. You can see that the TG is high as requested by the application. We are around 100 degrees, 95, 100 degrees, so we got our target. And here we consider the last application, the most challenging, is underwater application. We need to prepare polymers that are flexible, that are hydrophilic, that so can works well in underwater conditions. We prepared three different copolymeric system you see in this slide. And as you can see in this case, we want also to have a new polymer that can be 3D printed or UV cross-linked. As concerned these last properties, we decided to introduce along the macromolecular chains of our PBF itaconic acid, which is a bio-based monomer containing a double bonds that permit the cross-linking. An alternative strategies regards the introduction as terminal chains of acrylic groups that can permit also the UV cross-linking. So we are working on both strategies. The work has been done by Sant'Anna, INSTM, Unibo, and Maastricht University, and Polish partner. And here you can see some results got in Bologna in preparing the copolymers containing itaconic acid. As you can see from the video, we obtain a very flexible material that can be UV cured to have our cross-linked materials necessary to prepare our device for underwater applications. And last, the study regarding the interaction between our polymers and gamma radiation. Gamma radiation, as said by the colleagues, Deborah Puglia, is necessary to sterilize our packaging for biomedical applications. We saw that the dose of 25 kilogray does not affect at all the performances of our polymer, which maintains all the target properties at the optimal level. And here you can see the thermal, the diffractometric and the mechanical properties of the gamma treated PBF. As you can see, the properties are kept without any problem. So 25 kilogray does not affect the performances of our material. But what happens if we decide to use lower doses or higher doses? Here you can see that also the hydrophilicity is not at all affected by the gamma radiation, so this is good. Here the results that correlate the weight loss and the release of monomer according to the dose of gamma radiation used. As you can see, we have two competitive effects. If we use very high doses, cross-linking could prevail over chain scission. In this case, we reduce the amount of monomer release and we reduce the weight loss. On the contrary, if we chose the proper doses, we can promote the chain scission and we can recover a nice amount of FDCA that can be repolymerized, and this is a virtuous close of the loop in terms of enzymatic recycling. And that's all. Thank you very much for your kind attention.